When students first encounter fluid dynamics, the sheer complexity of moving liquids can make the mathematics seem intimidating. It is often taught as a specialized, standalone law of fluid behavior. Bernoulli's equation applies the conservation of mechanical energy to the movement of continuous fluids. This application requires specific boundary conditions. The fluid flow must be steady, incompressible, and non-viscous, and the analysis must follow a single streamline. This diagram shows the Bernoulli equation mapped over a simplified pipeline. These three distinct terms must sum to a constant, representing three specific types of energy density. We will derive this formula from first principles by converting discrete mass into fluid density and mechanical force into pressure. This framework explains the mechanics of Venturi tubes, atomizers, and Torricelli's draining tanks. For JEE aspirants, understanding the equation as a zero-sum energy balance prevents the calculation errors that come from rote memorization. Consider an incompressible fluid flowing through a horizontal pipe that suddenly narrows into a bottleneck. Because the fluid is incompressible, the volume flow rate, the cross-sectional area times the velocity, remains constant throughout the streamline. This diagram illustrates that relationship. The continuity equation, A1V1 equals A2V2, governs how this fixed block of fluid moves. As the cross-sectional area decreases in the bottleneck, the fluid velocity increases to maintain the constant flow rate. When we pause the flow inside the narrowest section, we see an increase in velocity, which means a gain in kinetic energy. According to the work-energy theorem, this increase in kinetic energy requires work to be performed on the fluid parcel by an external force. The continuity equation forces the fluid to accelerate, which converts the kinematics of flow into an energy balance problem. The standard work-energy equation for a solid object sums kinetic energy, 1/2 mv squared, potential energy, mgh, and the work done on the system. But we cannot easily track a single discrete point of mass moving inside a continuous, chaotic stream of liquid. Instead, we divide the entire energy equation by volume to analyze the energy per unit volume. Look at these standard energy terms. When we divide by volume, the cluster of mass over volume becomes fluid density, represented by the symbol ρ. This term, 1/2 ρ v squared, represents kinetic energy density. Similarly, ρgh represents potential energy density. The mechanical work performed by the surrounding fluid translates into the pressure term, P. Together, these three values sum to a constant. This derivation reveals the Bernoulli equation as the energy balance sheet for every movement within a streamline. We can test this balance sheet using a Venturi tube, which measures horizontal flow rate through pressure changes. Since the pipe is horizontal, the height of the fluid remains constant. Below the tube, the equation reflects this. Because the height does not change, the potential energy term cancels out on both sides. As the fluid enters the narrow section and velocity increases, the internal static pressure drops to keep the total energy constant. Torricelli's theorem applies the same logic to liquid exiting a hole at depth h in an open tank. In this scenario, both the top of the tank and the exit hole are exposed to atmospheric pressure. Because the pressure is equal at both ends of the streamline, the pressure terms cancel out. This simplifies the relationship to ρgh equals 1/2 ρ v squared. Isolating the velocity variable shows that the exit speed, v, equals the square root of 2gh. This formula is identical to the kinematic equation for a solid object falling freely from the same height. Complex fluid behaviors are solved by identifying which energy terms are constant and removing them from the balance. We can now observe a system where pipe width and elevation change simultaneously. As the fluid moves, these three energy types, pressure, kinetic, and potential, are in a state of continuous exchange. While the individual terms fluctuate, the total sum of energy remains fixed. In aerodynamics, this same exchange creates lift. The pressure differential caused by airflow curvature results in a lift force equal to the change in pressure times the surface area. Every increase in fluid speed is paid for by a corresponding drop in internal pressure or elevation. To solve fluid numericals, first map the streamline, then identify locked variables, and balance the remaining energy. Mastering Bernoulli's equation requires recognizing the energy accounting inherent to every fluid system.